Hey everyone, let's talk about the transverse electric polarization in a parallel plate waveguide. So you see here I've drawn kind of the basic geometry of interest here for what a parallel plate waveguide looks like. All right, so what we're looking at is a cross section here, and you imagine these little pieces of metal kind of extending infinitely in all these directions with a little gap between them, okay? And you notice I've drawn some coordinate axes here. So by convention in our textbook, the z direction will be kind of the direction of propagation that we care about. And along the y-axis here, we have a separation distance of little d. So I'm going to label here y equals 0 for the bottom half of my waveguide up here. And then my top bit, I'm just going to say y equals d. So there's our distance there. Now you notice the x-axis now has to point into the paper. And that's just by convention because these are the coordinate frames we've chosen. And I'm going along with your textbook here. So I have a right-handed coordinate system where if my fingers go into the page and I curl up into the y, my thumb points in z. So I have a right-handed coordinate system. So what I would like to do is somehow mathematically express the behavior of an electromagnetic wave inside of this waveguide. So remember, our governing equation, our ultimate equation of interest is the Helmholtz equation. So del squared E plus K squared E is equal to 0. Whatever happens inside of here, it must satisfy this equation. And there are going to be certain boundary conditions that we have to impose as well. So the question now is, how do I get started? Well, you have to just start kind of imposing certain conditions on what you want your solution to look like. For example, one simple thing I'm going to impose is the condition that my partial derivative with respect to x is equal to 0. And all that is saying is that nothing is changing along this direction into and out of the page. I don't necessarily have to impose this because hypothetically my wave could be propagating in any arbitrary direction. But all the information, you still have to kind of pick one of these directions. And all the information you get out of that solution will then apply equally well to all of the other just rotations on your coordinates. So there's nothing terribly wrong with imposing this particular assumption here. And I'm also going to impose a distinct polarization on my electric field. So what I'm going to write is my electric field as a function of y comma z. So it's not going to have any x dependence. I'm going to write it as x hat e sub x, and this little subscript x is probably redundant because there's really only the one polarization. So it's going to look like this. So that little subscript, we probably don't have to hang on to it because normally you would have an x and a y and a z, but if we're just going to impose the polarization along the x direction, then this becomes a little bit redundant. So I'm going to write it as just simply e of y comma z, and there's going to be a little x hat vector indicating that the electric field is polarized either into or out of the page. But again, if there were multiple components of this vector field, I would indicate them with subscripts, but instead I'm just going to leave off the little arrow to mean that this is the scalar function here representing the x component to my vector field. So it's a little bit of just kind of vector notation there. Right, so we have imposed a single polarization. We didn't have to impose this. We could have imposed the magnetic field to be along this direction. And those will also produce viable solutions, and that's okay. All of them can simultaneously be good solutions together if you superimpose them. So this is going to give us a particular set of solutions that we care about. So this is called the transverse electric. Let me write that out here. So by transverse, it means perpendicular to something, is what that transverse implies. So it's kind of like perpendicular, orthogonal, transverse. They all kind of mean the same thing. But basically, the z direction is sort of the direction of propagation we care about. There's going to be some flow of energy down this waveguide, and the electric field is perpendicular to it. So it is transverse to that direction of power flow. And so you'll see TE as kind of the indication there. And this is, of course, a prelude to what eventually we'll do is the transverse magnetic, which will be the TM polarization, and that is fine as well. So now the next, I guess you could say the final real assumption we're going to impose on this is I want some kind of expression of energy propagating down that way as a wave. So I'm going to just assume This is a wild assumption. Maybe it'll lead me somewhere, maybe it won't. And of course it will lead us somewhere because we have the benefit of hindsight here. But I'm just going to assume that my function here for my electric field is going to look something like the following. E of y, e to the minus j, k sub z, z. In other words, I'm going to have some functional dependence this way, but whatever the dependence is in this direction, it's going to take on this sort of waviness. I don't necessarily know what this particular constant here is going to evaluate to in terms of my Helmholtz equation, but this is the assumed form of the equation that I think will give me a satisfying picture of the solution or the behavior of the waves down this waveguide. All right, and this will lead to some interesting interpretations when we get our solution. But just bear in mind, this is essentially a wild guess. And as long as it satisfies the boundary conditions, it's good. And if it doesn't allow me to satisfy the boundary conditions in any meaningful way, then it's a bad assumption. But if I can get a solution to the Helmholtz equation and my boundary conditions, I have the solution. And all this means is I was smart enough and insightful enough to guess the proper form of that solution to make the minimum amount of assumptions to get that answer. So this is all we're going to presume here. So what do we do now? Well, the first step is just take this here, plug it into the Helmholtz equation. So how does that work? Del squared E, because if this is a vector, but we're only going to have the one scalar component to it, it's going to be the following: del squared E times x hat. So the vector Laplacian is going to be a scalar Laplacian pointing along the x direction. And the x derivatives here are 0. So what this will evaluate to is the following: partial squared with respect to y squared plus partial squared with respect to z squared E. So remember, this is the scalar E here. So we're just going to distribute that. And what you'll get is the partial derivative with respect to y here is going to act on this little separable bit here. So you notice we've kind of imposed a bit of a separation of variables here. So this derivative will act on the y function dependence here. And this derivative is just going to act on this complex exponential to give me a little kz squared. So essentially what I'm going to get is the following. I'm going to get e double prime, so because it's just a function of y. So it's the second partial with respect to y, times e to the minus j k sub z z. So that's the first partial derivatives here. And then my second derivatives along z here, or I should say the first second partials and the second partials. So what I will then get is plus negative j k sub z squared times e to the minus j k sub z. Okay, so that's just this little guy here. And I also have to add this little k squared e up here. So I'm just going to go ahead and say del squared e plus k squared e is going to evaluate to this little term here plus a k squared term. So I'm going to drop the x hat for now. We're just going to leave it as implied. And basically what we'll get is the following: e double prime. And so this is going to give us a minus k sub z squared. Times e, excuse me. So there's I'm going to factor out this little term here. So these guys I'm factoring off here. So I'll get e double prime plus this. So e to the minus j k sub z z, so that's the first term, and then plus k squared times that e to the minus j k sub z z. So I took this little term and I just added the k squared here. And you could also kind of in the back of your mind just remember there's an x hat implied here, and that is all equal to 0. So again, these are vectors, so there's an x hat here, but we're going to kind of drop that for now because we don't have to keep writing it. And this is all now going to be 0. So the del squared is this term. Let's just kind of emphasize that a bit. So this bit here is my del squared e. And then this over here, all of this is my k squared e. like so, in my Helmholtz equation. So the first thing that kind of immediately jumps out is obviously these guys divide out because everything here is 0. So that's a common factor that disappears. So I'm going to rearrange a few terms and get the following. E double prime, remember this is a function of y. So the second derivative of this function here with respect to y, minus k sub z squared times e plus k squared e equals 0. So we'll rearrange another little bit. This implies, let's just go ahead and write this a little more explicitly. Partial squared e with respect to y squared is equal to k squared, this is going to be minus k squared plus, let me get my signs correct here, k sub z squared, like so, times my e of y. Okay, so I hope you're able to follow along with all that. I got a little bit of messiness here. But you can see this is now just the Helmholtz equation, finally spits out all of these terms and simplifies, and I get a nice little ordinary differential equation. Okay, so you notice the second derivative of e is equal to this constant here times this. So I'm going to do a little substitution. I'm going to call this k sub y squared. Okay, so we'll have a very simple relation that is implied by this, where it says k squared is equal to k sub y squared plus k sub z squared. So you notice if I solve for k sub y, oh sorry, that should be a negative there. So you rearrange this and I'll get this term here being implied. So I haven't done anything sneaky, I'm just giving this little term here a name and showing that it'll satisfy this here, which is pretty convenient and straightforward. So this is relatively easy to solve. It is an ordinary second order differential equation, and we get the following solution. It looks like the following. E of y is going to look something like this. A sine of k sub y, y, plus b cosine k sub y, y. So this my little y dependence here that we assumed up here has to satisfy this. The Helmholtz equation has told me that that's necessarily what it must be. So let's go ahead and write out our total solution. I get my electric field, E, is equal to x hat, and I'm going to get something like the following. A sine of ky y plus b cosine ky y. So you notice I'm just kind of plugging into the general vector form here. And then again, e to the minus j k sub z, like so. So this is now anything of this form. If I assume this little piece of my z dependence, this is necessarily what pops out when I plug it into the Helmholtz equation. So I'm going to make a little bit of a quick notational jujitsu here. This k sub y and this k sub z, I'm going to give them new names. It is very instructive to think of them as kind of like these wave vector components. But later on, when we get our solution, the subscripts are going to get in the way. So this is a little deviating from the book here, but I'm going to call this gamma. And this guy over here is going to be beta over here. So my little relationship here becomes k squared is equal to gamma squared plus beta squared, like that. So I'm going to call this beta. This is going to have a name. This is the transverse propagation constant, whereas this is going to be the longitudinal propagation constant. So that's why it helps to give them these new names here. Okay, so we are at this point. So what can we do from here? Because I haven't really narrowed things down much. This is just the solution that comes out of the Helmholtz equation if I assume my z dependence in this form. But I don't really have any clue what these a's and b's are supposed to be. So for that, we now have to impose boundary conditions. So I'm going to kind of just slide this off to the side here. So my first boundary condition, and I guess you could say my second boundary condition on top of that, there are going to be two boundary conditions. Basically, my electric field, because it is tangential to this metal, has to be 0 at this point. And up here, it also has to be 0. This is just a fundamental law of physics and electromagnetism. The tangential component of an electric field is always 0 along a metal conductor. So my electric field is tangential, it's parallel to these plates, and so it has to be 0 at these edges. So you write that by simply saying E of 0 comma z is equal to 0. That's my first condition. And then I write E of d comma z is also equal to 0. Those are my two boundary conditions. So you look at my general form here. So let's write this out. E of y comma z. So I'm just looking at the scalar function here is equal to a sine of gamma y plus b cosine of gamma y e to the minus j beta z. So I've just rewritten this expression here, but in terms of my new little propagation constants. And I'm going to now impose my boundary condition. E of 0 comma z is equal to, so you notice if I put in a 0, I'll get a 0 for my sign here. So I get an a times 0. And if I put in a 0 here, I'll get a 1 plus b times this guy here, e to the minus j beta z is equal to 0. Okay, so that's a common factor. That's not going to change anything. And you immediately see 0 plus b equals 0, and I get b equals 0. So my first boundary condition says this b must be 0. I'm not allowed to have this cosine dependence, because that would imply an electric field starting at the maximum here and then changing away from here, the plate here. Whereas the sine, it starts at 0 at this point here. So I'm allowed to have a sinusoidal bit here, but not a cosine. So immediately that means this guy disappears. And I am now left with the following. E of, let's add a little more space. E of y comma z is equal to a sine gamma y e to the minus j beta z. So my first boundary condition threw away the cosine, and now this is what we have left over. So I'm now going to apply my second boundary condition up here, and I'm just going to say E of d comma z is equal to a sine gamma d e to the minus j beta z is equal to 0. So I just plugged in a d for y. And again, the same thing happened. This little term here, this factor can't change anything because it will, it's a common factor. So that's going to go away in 0. And I am basically just left with a sine gamma d is equal to 0. So what does that tell us? Well, first off, this a factor here, it can be what anything it wants. It just kind of scales the system, either large field intensity or small, but it doesn't really do anything to the functional form of the system. So that term can divide away because of the 0 out here. And we are basically left with gamma d is equal to the arc sine of 0, which means, what's the arc sine of 0? What are all the angles where I can get 0 essentially? And you get n times pi, where n is equal to 0, 1, 2, 3, 4. Any integer multiple of pi is allowed. Except, however, you got to be careful. This 0 is technically a solution, but all it will do is make this sine term also 0, which then makes my electric field 0 everywhere, which is trivial. So I'm going to throw this guy away. It's technically allowed, but it's not interesting. It just literally makes everything 0 and nothing's happening. So it's going to be any positive integer here. And in fact, you could add plus or minus, but all that would do is add a plus or minus out here onto my leading coefficient, which is just the same as saying my electric field jumps either positive or negative. So really, we're just going to care about only the positive integers here. So what you get is gamma is equal to n pi over d. And because this is an infinite set of possible solutions, I'm going to add a little subscript n here. Any value of this gamma here that satisfies this condition will be an allowed solution to this entire differential equation and satisfy my parallel plate waveguide. So each of those solutions, they are called modes. And we'll see a little bit more of that in a second. So remember now, we had this relationship back here where k squared is equal to gamma squared plus beta squared. So I have k squared is equal to gamma squared plus beta squared. So if I have this infinite set of possibilities for my gamma, then that is also going to imply some corresponding betas here. This term here is fixed because it's part of the Helmholtz equation, right? Remember, k is omega over c. So that's inherent to the Helmholtz equation, and it won't change. It is fixed and determined by the frequency of excitation I impose onto the system, but these two propagation constants will then kind of vary with respect to each other. So what we tend to write is the following. I'm going to write beta sub n is equal to the square root of k squared minus this gamma sub n squared, or we can simply write n pi over d squared, like so. Okay, so as long as I have, these are my allowed propagation constants. As long as they satisfy any of these values, I will have a solution to my parallel plate waveguide. So this now tells us something very interesting, because this is an infinite set of solutions, and they all satisfy the boundary conditions, at least for the top and bottom of the plate. So what does that mean? Any solution will, I'm satisfying the boundary conditions, I satisfy the Helmholtz equation, and there's an infinite set of them, which means any linear combination of them is also a solution. So the way you write this out is as follows. I would say my E of y comma z is going to look like the following. I'm going to have a summation from n equals 1 to infinity, a sub n, sine of gamma sub n y e to the minus j beta sub n z. Okay, and so this is the general solution for the electric field profile propagation down my parallel plate waveguide. And you see it's basically a Fourier series. And that tells us a lot of interesting things about the nature of the waveguide propagation. So any one of these terms is a solution. And remember, the only condition is this has to be n pi over d, and then beta sub n squared is equal to k squared minus gamma sub n squared. So this condition must be met. This one just sort of follows, and that's what I plug into each of these terms. Okay, so each one of these is a solution, which means any linear combination of them at all whatsoever is also a solution. And so these a sub n's, just remember, these are electric field amplitudes in a sense. So this would be, they have units of volts per meter, right? So each one of these little terms in this summation here is a mode to the parallel plate waveguide. So I'll create some animations to help you visualize what you're seeing there. But that's the basic idea. So burn this equation into your mind. It's essentially a Fourier series of possible solutions. And we'll talk a little bit more about what they entail in the next lecture.